Okay. Awesome. So let's get going here. Look at your question. We're going to be talking about. So we have two sections we're going to do today. First section is called, basically the long name is integration of rational functions by partial fractions, but typically we just want to label this as partial fractions. Okay, well, what is partial fractions? What do we mean by a partial fraction? Well, the book starts out, and I'll start out as well, by kind of demonstrating something really fast, that given a couple of rational functions that are together. So we have 2 over x minus 3 minus 1 over x plus 2. Right? If I just gave you this problem, right? Let's say that we put an integral around it, right? And I asked you to evaluate this integral. Would we be able to do this at this point? What do we think? Yes, we could. Why? Yeah, so exactly. So these are both pretty easy u subs to plug into a natural logarithm, right? Like I can take u as x plus 2 or u as x plus 3 here. And then, so du is going to be something, but then I might just get 2 times 1 over u. And then the integral, that's going to be natural log. So I can do both of these. I know how to do both of these, okay? But let's take these two fractions and let's combine them together, okay? So what I mean by that is let's give them a common denominator. Give them, same denominator, just one fraction instead, okay? So if I want to give these guys a common denominator, what do I need to do? What do I need to multiply this one by? So we want to do x plus 2 over x plus 2, right, in specific, right, times 2 over x plus 3, because I can't just multiply by x plus 2, because then it would be the same thing, okay? Minus, and then we need to multiply top and bottom of 1 over x plus 2 by what? X plus 3. And this is going to give us 2 times x plus 2. Just going to 4 over, I won't worry about x plus 2 times x plus 3 minus, and I'll just put these parentheses here so we know to subtract both parts. We just have x plus 3 again over x plus 3. Okay, cool. So whenever I do this, right, I want to have, what's going to happen, right, is I can take the top and combine it, right? So I'm going to have 2x minus x, and I'm going to have 4 minus 3, gives me plus 1, over, now maybe we'll FOIL this down here this time, make it look a little more, forget a little more where we came from. But let's do x times x is going to be x squared, 2 times x is 2x, x times 3 is 3x, so that becomes 5x, and then 2 times 6 is plus 6. Okay? Okay, so this is the same thing as this expression right here, right? Now, quick mention, by the way, there were a couple tests where you had x plus 1 squared, but then we said that someone said this is the same thing as x squared plus 1 squared, which is not true. Remember, don't forget about how to multiply. Like if you have a binomial, you have to FOIL it, use FOILing. Or if it's square root, you can't just take the square root of each term, okay? So we need to keep track of that, but want to mention it while thinking about it. Okay, so again, let's go back to what we were saying. This, if I was integrating this, I would know how to integrate this guy. What if I asked you to integrate that function, okay? would you know how to do this? Right? Would you be able to do this easily? Right? Well, we wouldn't. First thought is maybe I could do a u sub, right? So I'm going to let u be x squared plus 5x plus 6, maybe something similar to what we would do over there. And then, but du is going to be 2x plus 5 times dx, right? But I don't have 2x plus 5. I don't even have 2x plus 2, right? Because if I had that, maybe I could make it work, but I don't have the same thing that I have on top. So unfortunately, I have an issue. However, we just established that this is the same thing as this guy, correct? We know how to integrate this one. So what we can do is, so this in this process, we started here and got to this, but what partial fraction decomposition says is, let me take this guy and bring it all the way back to here, to something I can integrate, okay? Now this only works in particular for these rational functions, right, where I just have basically a polynomial over a polynomial. We don't really want square roots in there as much. You don't want e or sine or something. Now there is a section in the homework where they want you to do a u sub, which will turn it into a rational function. But if it's just like, you just have to be wary sometimes there. And generally you can't use partial fractions unless it looks like this. Okay, so that's exactly what we're going to be doing today. We're going to go practice through some examples and kind of see how this works, or how we would do these sorts of problems and work it out. So I think to demonstrate, I'm going to, I'll just do some like the book problems here. Not necessarily in their examples, but just some of the ones in the section, just to give us a good idea. Okay, so first, start with this first example. Okay, so we're going to learn how to use partial fractions, right? And there's going to be 4 cases we're going to lay out. The first 3 are going to be the ones that pop up the most. The 4th is just like if you have it potentially. But we're going to start with the simplest one. Okay, so I'm going to give us the function. We want to integrate x. Let's see, we'll do minus 6 over x squared plus x minus 6. Okay, so I want to take this thing, I want to find the integral of it. Okay, now, again, maybe I'll put it next to it just to make sure we can do that. I could try to do u sub on this, right? But there's an issue in this, in the fact that if I let u be the bottom, what is du going to be? What is it? 2x plus 1, right? Which is definitely not x minus 6, not even a multiple of x minus 6, right? So we kind of run into an issue. Okay? So doing u sub won't necessarily work out for us right now. Okay? So the idea is maybe I can take this thing and break it up into smaller parts, and then I can do the integral of those smaller parts, and that altogether makes up the cohesive whole that is this fraction. Okay? So if I want to break this up into a fraction, right, or smaller fractions, I would hope that my denominator can do the same thing, right? Because we saw in that one that we took x plus 3 and x plus 2, and those together gave me x squared plus 5x plus 6. So ideally, I'd want this to break up into 2 different pieces as well, right? So we want to try to factor this. So we're going to factor x squared plus x minus 6 as far as we possibly can. Okay? Right? So this is a quadratic, right? So how many terms is this going to factor into? Not 4. It's going to be 2, right? If it was 4, then it factor into 4, or it could factor into 4 at least. But if there's 2, then it can only factor into 2. Okay? So what are these 2 terms going to be? Anybody remember how to factor a polynomial? Yeah.
Plus 3x minus 2.
Plus 3 and x minus 2. Good. Okay, let's think about why that is. That's going to be because x times x is x squared. X times, so again, we want a 4, right? Think about 4 like this. X times x is x squared. X times minus 2 is the outer, it's minus 2x. 3 times x is 3x. 3 minus 2 is 1, right? So we get x. And then 3 times minus 2 is minus 6. So that works completely. Okay, so this is going to turn into the integral of x minus 6 over x plus 3. Okay, so we factored that, right? So we would hope that this expression can turn into smaller pieces. One smaller piece having x plus 3 as the denominator, and the other smaller piece having x minus 2 as the denominator. We know what these constants are. Anybody tell me what these numbers are going to be? You could guess and test it, I guess, but I imagine you probably wouldn't know off the top of your head, right? And so that's okay. We're going to actually need to work to figure out what those are. But for now, I'm going to call that one A, I'm going to call this one B, right? So I'm going to take this fraction to integrate it. I'm going to split it up into pieces. We have A over x plus 3, and we have B over x plus 2. So let's integrate, or not, sorry. Let's try to figure out what those are, right? So remember, we want A over x plus 3 and B over x minus 2 to be equal to x minus 6 over x squared plus x minus 6, which is the same thing as x plus 3 times x minus 2. Okay. So we just need to figure out what those numbers need to be in order to make this work. Okay. Now I'm going to do a step first, right? Because I don't like dealing with fractions. If I don't have fractions to deal with, that would make my life a little easier. So I'm going to take both sides of this, and I'm going to multiply by x plus 3 times x minus 2. Can anyone tell me why that is? Good. So this contains, yeah, it would cancel out all the denominators. It's definitely going to cancel out this one. And then this x minus 2 is going to be taken out here, and this x plus 3 is going to be taken out here. Okay? So we're going to be left with, once I multiply, so I'm going to get A times what? X minus 2 plus B times what? X plus 3. Thank you. This is going to be equal to x minus 6. Okay, from this point, you could really approach this a couple ways. I'm going to show you both. I'll start with the one that the book does, and I'll show you the one that I like to use because I think it's a lot easier. So, method number 1 here. We want, right? We ultimately want whatever multiplies over here, right? So let's distribute things real fast, right? So if I distribute this A to this x minus 2, I'm going to get AX minus 2A. And if I distribute the B here, I'm going to get plus BX plus 3B equals x minus 6. Now, first, right, you might think, oh, well, there could be so many, I mean, how do I solve for that? How do I work this out, to pair these things together? Well, it's as simple as just saying, okay, AX and BX. Those both have an X on them. So whatever those add up to, right? Because if I add AX plus BX, I get A plus BX. That needs to match up to this X on this side, right? So whatever the coefficient of this X is here needs to be the coefficient of this X on this side, right? You want those to be the same. We're not working with something, like too crazy here. It's just saying what's the coefficient of this one? It needs to be the same as the coefficient on this side, okay? Then we can take minus 2A plus 3B, and we can compare that to the minus 6 over here, right? So again, let me illustrate. A plus B should match up to the 1 in front of this X, right? Because it's in front of the X. whatever's in front of the x here should be in front of the x here, right? You want those to be the same. And also, whatever is the constant term on this side needs to be the constant term on this side. So we can set up a system of equations, right, where we have a plus b needs to be equal to 1, right, because we want the coefficients in front of the x to be the same, and we want negative 2a plus 3b to be equal to minus 6, right, because we want those constants to be the same, okay? So I have two equations with two unknowns in them, right? So I should be able to solve this. This is a system of linear equations, right? So I need a suggestion. What should I do to solve for these? What method might be used? Substitution? Okay, that sounds great. Absolutely. Which one are we solving for? Like which one we're gonna use for substitution here? We're gonna start with this one, or are we gonna start with this one? Yeah, probably the first one. Probably be a bit easier, right? You want to solve for B or solve for A? A, okay. So we're gonna get. So what is A equal to? If I solve 1 minus B. Now, right? What substitution says is I want to take that. What A is, right, in terms of B, and then I'm going to take that and I'm going to put it into the other equation, right? Which is going to leave us with negative 2 times 1 minus b plus 3b minus 6. I'm going to get negative 2 plus 2b plus 3b equals minus 6. Okay. I'm going to add this negative 2 over, or add 2 to both sides to cancel that. And we're going to get 5b equals negative 4. So what is b going to be? If I can see this one, please. Negative 4/5. Good. So b is negative 4/5. Okay. So if b is negative 4/5, what does that make a? 1 plus 4/5. Good. And what's 1 plus 4/5? 9. Thank you. Okay, now let's just check and make sure those work with our equations, right? So 9/5 minus 4/5 is 1. Okay, this one might be a little bit more. Let's see. So negative 2 times 9 over 5 is negative 18 over 5. So I'll write that for a moment. Negative 18 over 5. And then 3 times negative 4/5 is negative 12 over 5. What's 18 plus 12? Was it?
30.
30, yeah. We get negative 30 over 5, and what's negative 30 over 5? Negative 6. Good, so it works out. It checks out, right? So we get A here, and maybe I'll go ahead and bring this up. So A is the same thing as negative 9 or positive 9/5, sorry. So we get 9/5 over x plus 3, and we'll have plus b, which I'll go ahead and it's minus 4/5, right? So I'll just take that 4/5 and pull it on here. Okay, fantastic. So we get here, right? Which this is an integral I can definitely do, right? That constant on top just can be set on the side at that point, right? But once we have it, we can get an accurate answer. And I'll finish that in a sec, but I'd like to go ahead and show you the other way that I would prefer to do this problem. Okay. So what we have here in this expression up here is something that should work for any x you plug in, right? That both sides should be equal to each other, right? So what we can do is we can take specific values of x and plug them in, right, to see what relationships we have, right? So the best options in this case, in particular, are what if I did x equals 2? So what do I get if I take x equals 2 and I plug it into this? What am I going to get? So we're going to get a times 2 minus 2, which is what? It's 0, right? So we get 0, so I'll write it a times 0 plus b. What's 2 plus 3? 5. Yep, good, thank you. And what's 2 minus 6? -4. Okay, so this says that 5 times b equals -4. So what is b? -4/5, right? Okay. What's the other option that I plug in? -3. Good. And that is because it's going to make this term 0, right? So when I picked 2, it made this part go away, so a was gone. And when I plug -3 into this part, b is going to be gone. So I'm going to be left with a times what? -5. And then plus b. Now this should be times 0, right? Because -3 plus 3 is 0. Equals, what is -3 minus 6? Right, so we get -5a equals -9. So what is a? 9/5. So that is our answer. Now, what I will say, we're going to get into some more complicated situations, as you might imagine, where we won't just have these like linear factors, right? So I don't just have x minus 2 and I don't just have x plus 3, but I might get into quadratics, right? Which still works a lot of the time, but also I might get into situations where I don't just have x minus 2 to the first power, but I'm going to have x minus 2 to the second power, to the third power up in here as well. And so that causes a bit of issues whenever we're dealing with, when we're trying to work with this method here, just because you're going to end up canceling out maybe more terms than you're hoping for, right? And so it's a little bit harder to get some of the values, which I might highlight that when we get there. But use this if it seems like a pretty easy situation, or you just have, there's none that are alike here. But this one always does work. So does that make sense at that point? We good here? Okay. 2 methods. I don't care which one. This one's probably the safer one, but this one just takes a while sometimes, right? Because sometimes you don't just have 2 pieces. Sometimes you have 5 pieces, right? And so you're going to have to solve 5 equations with 5 unknowns, which just is not an ideal situation, right? But sometimes we do have to. We do have to use them. Okay. Well, let's finish off this integral real fast, right? So again, what we could do is we could take out each of these constants on the side, and so we just have 9/5 times 1 over x plus 3 and 4/5 over x minus 2. And we could do a u sub for each of them, right? But if, for example, on x plus 3, if I let u be x plus 3, what is du going to be? 1dx, right? So it doesn't, that plus 3 and this minus 2 don't affect anything, right? So I can just integrate them as I would typically the natural log. So on this one, I'm going to get 9/5 times the natural log of x plus 3, and make sure that's in absolute values, minus 4/5 times the natural log of absolute values x minus 2 plus 0. Okay. Now, depending, I think maybe the book will kind of take the pieces and combine them together. Because you can, obviously I can take those kind of exponents and then use logarithm rules, but in general, that's going to be my answer. Okay. So, yeah, how do we feel about that so far? Not too bad, hopefully. It should be decent, nothing too terrible. Sounds good. Okay. Let's see. Next. Okay, so let's go ahead and move on to example number 2. This is based off of for number 4 part A in the book, though it doesn't. On those first 2 problems, it doesn't have you go as far. So I'm going to take them all the way. We'll find the actual answers to them. Okay, so we'll call this example number 2 for our purposes. We're going to have the integral of x to the 4th minus 2x cubed plus x squared plus 2x minus 1 over x squared minus 2x plus 1. Okay, so this is going to cover a couple of things here, so we'll elaborate on both. But let's notice what happened on our first couple of problems that we did, right? On the very first example, kind of introducing the concept, when we had the 2 pieces, whenever they combined together, right, I had a number over x plus something, a number over x minus something, whatever it was, and that combined together to give us some linear term, right, x minus 6 or x plus 1 over the denominator, right? And in this case, we're starting off in a similar situation, right, where I have a term that's just x to the first power over something that's a higher power, than that, okay? And in that case, that makes all of this work completely fine. However, and I know this is going to factor differently, but I'm going to say as a hypothetical case at the moment, okay? Let's say that I just ignored the degrees of this problem and just said, okay, let's split it up and do the partial fractions, okay? So then this is going to be the same thing as a over x plus m plus b over x plus n of some sort, right? Well, if I try to solve this, right, if I try to turn this into this, I'm going to run into a lot of issues, right? Which will become apparent here in a sec. Yeah, I won't worry about factoring real quick because I want to highlight this part rather than the other part. Is going to be x to the 4th minus 2x cubed plus x squared minus plus 2x minus 1 over x squared minus 2x. Okay, so let's say I just split it up as I did the last one and try to work it out. Okay, well, I might be able to cancel out my denominators using the same thing. So I might have a times x plus n plus b times x plus m. And then I'm going to get x to the 4th minus 2x cubed plus x squared plus 2x minus 1. And so maybe we get to this situation, right? Similar to what we got to in this case, right? Where we could split it up either way. But there's an issue here. What's wrong with this? What is it? Yeah, so notice it has to do with the powers here, right? So remember on this one, I had whatever the highest degree was over here should match whatever the highest degree is over here, so that I can effectively combine, make these equations and solve this, or work out something like this. But they need to be the same, right? The issue here is I have, and especially if I kind of factor this out, I'm going to have, or distributed, combine these together. I'm going to have, let's say, a plus bm. It's going to be x to the 4th minus 2x cubed plus x squared plus 2x. Right? There's an x term, sure. There's a constant term, sure. But where's everything else, right? I should be able to compare to each of these, right? To be able to solve the equation out, right? Because there's no way, right? Even if I were to compare these and say, oh, well, a plus b is 2, am plus be m equals -1. Whatever those numbers are, if I plug those in, I'm not going to get a 4th degree polynomial. I'm going to get a 2nd degree, or a 1st degree, right? Which is a problem. This does not work. So I cannot start out this problem until I fix something first. Okay? The degree in these partial fraction problems, maybe I'll write this. Partial fractions. Degree of numerator must be less than the degree of okay. So if I'm going to use partial fractions, I need the numerator to be a smaller power than the denominator is. Okay. Not that I can't use it at some point in the problem, perhaps, but I can't start off with it. Okay, so we're in a situation where, on the first one, we didn't have to worry. It was already like that, so we're good. But in this situation, I have a much bigger power on top than I do on bottom. Not much bigger, but still bigger, right? So I need to figure this out. I need to somehow, if I want to use partial fractions, I need to take this expression and split it up in such a way that I might have some piece like that kind of takes care of the bigger parts, but then I have a fraction left over that's going to allow me to use partial fractions. And what I mean by that is I want to be able to write this as, maybe when I divide it, I'm going to have some x squared term, some bx plus c term, and I'm going to be left with something over x squared minus 2x plus 1. Because theoretically, if that's bigger, then it should be able to, I should have like some part that goes into it normally and then have like a remainder, right? Kind of division, right? So I'm going to be dividing these two, right? So who remembers how to do long division? I hope most of you do, because we're going to need to do long division. So, okay, but we'll walk through it real fast, okay? So before I start this problem, I need to take x to the 4th power minus 2x to the 3rd power plus x squared plus 2x minus 1, and I need to divide it by x squared minus 2x plus 1. Okay, so how these long division problems work, if you remember, is that I use the first term of my polynomial as kind of a catalyst for everything. I would take that term and I would compare it to the first term of the expression I have at the time, right? So first I'm going to say, how many times, or what do I need to multiply x squared by to give me x to the 4th power? So what do I need to multiply x squared by to give me x squared? So I'm going to write an x squared term right above that. Okay, so then I take that x squared term and I multiply it to each of these 3 pieces. So x squared times x squared is x to the 4th. X squared times 2x is 2x to the 3rd power. X squared times 1 is x squared, and then make sure that the signs stay consistent here. And once I have that, right, I multiply the x squared by the whole thing. I'm going to take it and subtract. I'm going to subtract that expression, right? Because I said, okay, that goes into an x squared times. So let me take off this piece and move on to the next part. So what's going to happen when I take x to the 4th minus 2x cubed plus x squared minus x to the 4th minus 2x cubed plus x squared? So all of that cancels, right? So we're just going to be left with, this is just 0 here, and we have 2x minus 1. Okay, now normally, if this didn't completely cancel out, right, if I had an x cubed term left over, I would say, how many times does x squared go to the x cubed term? And then if there's an x squared term left over after that, I'd say, how many times does x squared go into that term? But obviously those are both gone, so I can't do that. And since 2x is of smaller degree than x squared, I'm done. I have to leave it at this point. I'm done with my long division. Okay, so I end up getting that this fraction is equal to, we're going to have x squared, because that's what we got when we divided, plus 2x minus 1 over x squared minus 2x. Yes. Okay, do I know how to integrate that? Good, I do. Can I use partial fractions on that? Yes, we can, absolutely, because now the degree of the numerator is smaller than the degree of the denominator. So that's exactly what we're going to do. Any questions on that? Please don't feel free to ask. About? Yes. You still have to use this. You still have to do long division. They can't be the same, they have to be less. Now it could be one less, it could be two less, it could be many less, but it has to be less. You cannot have them equal and it cannot be greater. Okay, so if you come to a problem and it's like x cubed plus something over x cubed plus something, you have to use long division first before you do the problem. Okay? Okay. Good. So let's continue with this guy. Okay, so again, we said the integral of x squared is easy. What's the integral of x squared? 1/3 x cubed over 3. Okay, so we're gonna save him. We'll hold him on the side for now. He'll come back eventually, right? But that's our integral there. So we'll leave that. Let's focus on the integral of 2x minus 1 over x squared minus 2x plus 1. Okay. So again, maybe it would be worth it to try to see if you can do a u sub, but it still doesn't work in this case. It's very close. We get 2x minus 1 on top, and then if you take the derivative of the bottom, it's 2x minus 2. So it's a little off, but it still would be better to go ahead and use partial fractions here. But we're going to run into a bit interesting of a scenario in this case, right? Let's think about why that is. We need to factor x squared minus 2x plus 1. How does that factor? This is a perfect square. Okay? So this is a bit different, right? So we're not just dealing with two different linear factors that I can just split up easily. I have this x minus 1 squared term. You may think though, you're like, oh, well, obviously this is going to just be a over x minus 1 plus b over x minus 1 dx. But this is incorrect. You will not get the right answer if you do this, okay? And it's just because of the nature of that little repeated root there, it gets a little wonky, right? So if you try to split it up as the linear factors like you did here, you can't do that, okay? What we have to do is one term is going to have x minus 1, but the other term is going to have x minus 1 squared, okay? So again, let me repeat that. If you have a denominator, if in your denominator you have a linear factor that's repeated, right, to a power, then you're going to take a number over the first term, so a over x minus 1, b over x minus 1 squared, and let's say it goes to the 5th power. Then you would have c over x minus 1 cubed plus d over x minus 1 to the 4th plus e to the over x minus 1 to the 5th power. Okay, so you have to cover all of them, right? All of them have to be acknowledged in order for this to work out, in order for this to make sense. Okay, so this is going to split up into this, right? But we can go through the same process, right? To still find the a and b, so nothing changes after that point. But it's very crucial that we understand why we need to write it like this rather than doing it like that. Okay, so does anyone need further explanation on that? Is that good? Does that make sense? Okay. So again, if it's a linear factor, right, or if it's just there like to the first power, right, if you just have 1x plus 3, 1x minus 2, 1x or something, you're going to you're gonna just split them up into different fractions, call the thing. But if you have x, minus 5 or something to the third power, along with maybe those terms, then you can split those up just fine, but that x minus 5 to the third needs to have 3. It needs to have a over x minus 5, b over x minus 5 squared, and c over x minus 5 cubed. Okay, so you need to run through all of them. Okay, so in this case, we have 2x minus 1, so we're going to have both. Okay, so again, we repeat the same process, so we're going to have a over x minus 1 plus b over x minus 1 squared equals 2x minus 1 over x minus 1 squared. Okay, so what should I do maybe to simplify this? Get rid of those fractions. What should I do? So you're thinking on the right track, but if you do both x minus 1 and x minus 1 squared, it's getting a little excessive, right? Because at that point, you're multiplying by x minus 1 to the third power, right? So you would cancel out everything, but you'd also have 1x minus 1 left here and 2x minus 1s left here, which is more than you need, right? If I just multiply this thing by x minus 1 squared, that'll cancel everything I need. It doesn't make it more complicated than it needs to be, right? So x minus 1 squared over x minus 1 squared just gives me 2x minus 1. X minus 1 squared over x minus 1 squared again is just b. And a over x minus 1 times x minus 1 squared is a times. Okay, so again, if you can feel free to use this. I just wanted to show real quick. Just for the sake of when we get to the later ones, I will probably stick to maybe just demonstrating this way, but this one's actually a lot simpler, and we'll see why. Right, so I'm going to get ax minus a plus b, and that's going to be equal to 2x minus 1. Okay, so who can tell me what my two equations are going to be in this case?
A is 2.
Good. Look at that, nice and easy. A just has to be 2 because it's the only x term left, so it has to be 2. Okay, and what's the second one? Yeah, negative a plus b is -1, or b minus a is -1, but a is 2, right? So we get b at minus 2 equals -1. So what's b? So it's -2, so if I have to do both sides, I get 1. So a is 2, and b is 1, and so that's going to translate over here. I'm going to get the integral of 2 over x minus 1 plus 1 over x minus 1 squared. Okay. What's the integral of 2 over x minus 1? What do we think? Yeah, fantastic. So at this point, I don't really mind if you use that too much, just to say, oh, well, it's x minus something or x plus something. So the integral is just going to be the natural log of that thing. But if you have like a 2x minus 1 or 3x or something, then be a little bit more careful. But with that, but in these cases, right, you can just. How about this one? Not true, actually. Right? Because we don't have it, right? We have the second power now, right? If it was the first power, it would just be the natural log of x minus 1, but we don't have the first power, we have the second power. Yeah, so maybe we'll think about a u sub here real fast just to see it. So u would be x minus 1, what's the u going to be? Yeah. Dx, okay? Yeah, so we just get u to the -2 power. What do I get when I integrate u to the -2 power? Or I can write that as -1 for u. So in the end, I'm going to get minus 1 over x minus 1. So in the end, right, this was our starting problem here. The integral of this function is going to be x cubed over 3 plus 2 times the natural log of x minus 1 minus 1 over x minus 1. Okay? Yes.
For the where you guys did the use of, would you be able to just bring it to the top and then integrate it regularly?
Bring it to the top. You
So
mean?
do x minus 1 to the negative second top.
Yeah, absolutely. That you would, yeah, absolutely. In that case, you still technically need a u sub, but since it is x minus 1 and not like anything crazy in there, it would integrate as you did. Like this is the same integral as if it was x, except it's x minus 1 now. Again, if you just have x minus something or x plus something, you can integrate that as you typically would if it was just x. Right, so you could just bring it up to the top here, like Jacob was saying, x minus 2 to the negative second power, and then do it that way. But if you have something like 2x minus 1, or you have e to the x in there, or sine or something, obviously we need to be more careful, right? Watch out a little more. We can't just make those quick assumptions. Okay. Who get this? Good. Any questions on this? Anything? Okay, so maybe let's sum up what we've done so far. So let's see. So we've covered a couple of cases so far. Okay, first case is denominator is product of distinct factors to denominator is a product of and obviously this could both be kind of in the same situation, right? But it kind of works in a way where you say, okay, my problem is just a number one case. Okay. If my problem is just a number 2 case, maybe there's going to be some elements of the number 1 case. Or if you go to the next one, they kind of flow into each other. But essentially, we've covered 2 so far. The first one just says if they're distinct linear factors, which what does it mean to be distinct? What does it mean to have distinct linear factors? What do we think? Yeah, none of them are the same, right? None of them are going to repeat. Each linear factor you have is distinct. So I don't have 4x minus 1. I only have 1x minus 1, right? The second one says that we have a product of repeating linear factors. Now, sometimes when I say of repeating linear factors, some of them may actually be repeating, other ones may just be 1, right? But it includes repeating factors at least, so we need to be aware of that, okay? And that was that last situation we just did. We just covered that. Number 3. Okay, so we have linear factors, a bunch of linear factors. All we've done so far is working with linear factors. But obviously, we can have higher factors than that, right? Case 3 says denominator contains irreducible quadratic. Okay, so irreducible. What does irreducible mean? You can't, right? You can't reduce it. Maybe for the context of our situation, right? I can't factor it anymore, right? So if I took, at least into nice factors, obviously every quadratic can technically factor into 2 pieces, right? because, I mean, it should have two solutions, or like one solution repeated, so it can always repeat the two. But sometimes those just aren't the nicest ones to work with, right? Or you don't, your life would be a lot easier if you didn't try to factor, right? Like this one, for example, is gonna factor into okay. Now, do you want to work with this when trying to find your A and your B? No, because you're gonna have to worry about the root 5 and adding things together, and it's just not going to. It's not really going to be an interesting situation. Also, this one isn't even factorable in the real world, right? In our real integral space and what we're doing, right? So this one is irreducible for a different reason. I literally can't. Now, if you use complex numbers, this would actually be this, but again, that would just make life more complicated, and we're not talking about complex numbers in this class, so you can just throw that out the window, okay? So irreducible polynomial. That's the next situation we're going to talk about here. So let's see if we can find kind of a straightforward example that might help. Yeah, actually, right, the next one. Let's do that one. So this is for B in the exercises here, but I'm gonna just take it as one example. Okay, so we're gonna take the integral of x squared minus 1 over x cubed plus x squared plus x dx. Okay. So here's the question. Can I factor the bottom at all? At the moment. They all have an x in it. So this is the same thing as x squared minus 1 over x times x squared plus x. Okay. Now, yeah, so we can pull an x out, right? But we also have this x squared plus x plus 1 term, which does not have any real number solutions. I think it's like 1 plus or minus 3i over 2. In any case, we don't want to use it here, okay? Because that's going to give us trouble, right? So what do? I normally like to take everything and put it into linear factors so that I can just do a constant over that thing. But we can't do that now. So our only option is I'm going to take this thing and I can still take this x and I'm going to give it its own kind of separate term. So I'm going to a over x. But for x squared plus x plus 1, I don't just put b on top. I have to put bx plus c on top. Okay, so I have a over x, and then I have bx plus c over x squared plus x plus 1. Okay, so this is always the case. If you cannot reduce it any farther, then you have to have something times x plus something else on top of that bracket. Okay? Because otherwise it wouldn't work out as you expect it to. That's not going to make sense. Okay? Okay. Does that make sense so far? Just reasoning for that? Kind of follow through why I need to have something besides just one number up here. I need to have a linear factor. You can also, like this does extend, obviously, once you get past a certain point, if you're trying to introduce cubics and quartics and bigger polynomials and these problems, it does get a little more complicated than necessary for this class. But if you did have x cubed, right, plus something plus something plus something, and then on the top, and it wasn't like reducible, then you would have to have something x squared plus something x plus something on it, right? But let's just focus on the quadratic case right now. If for some reason it comes up in the homework, then sure, we can figure it out then. But at least in the extra homework, I wouldn't have a problem with that. But this is the basic idea. Okay, so if I can't reduce this, put a linear term bx plus c. Okay, good. So that's dx. Okay, now we need to figure out what a and b and c are still, right? So let's work that out. So we want a over x plus bx plus c over x squared plus x plus 1. And I want this to be equal to x squared minus 1 over x cubed plus x squared plus x. Okay, so what am I going to multiply both sides of this by to cancel out the denominator? Good. In the last example, we could use a smaller answer just because we had a repeating linear factor, but in this case, it's just best to multiply both of those denominators. And if you did that in the other one, it wouldn't necessarily be wrong, but just save you a bit of work. Okay, good. So that's going to leave us with a times x squared plus x plus 1 plus bx plus c squared minus 1. Okay, good. So again, you're going to notice, right, that one way to do these problems, you know, it's going to be pretty hard to do in this case. So we're going to try it. We'll probably have to avoid doing that, but that's okay because we always have our solid first method to do, right? So let's distribute this out, right? So what am I going to get when I distribute a? Yeah, a times 100 is a, right? What am I going to get when I distribute here? -1. Okay, so let's talk about, so how many equations am I going to have here? I'm going to have 3, right? I have x squared, I have an x squared term, I have an x term, and I have a 1 term. Basically, you say, okay, what's my highest degree, and then add 1 to it. That's how many equations. Because it's all the ones, all the numbers below that including 0, right? Or and including it. So my first equation, right, is going to tie every x squared term to the x squared term here. So what is that equation going to be? Squared, we need a plus b, right? Because that's the terms with the x squareds. We need that to be equal to 1. What's my next equation going to be? A plus equals 0, right? Because there's no x term over here, right? So if there's no x term, then I just need ax and cx to cancel out. Good. And then we have our constant term, which I'll just label C here. You can write 1 as well. Okay, what's that equation going to be?
A.
How about that? So that means, yeah, if I take this up, right, I can just plug a into both of these. Actually, it's going to give us c equals 1, and we're going to get b equals 2. Okay, does everybody see that? Okay, pretty straightforward. It's a nice example. Kind of comes together nicely. So we have a is -1, b is 2, and c is 1. So we're going to get the integral, right, of -1 over x plus 2x plus 1 over x squared plus x plus 1. Yes. Okay, so I'll rewrite that integral over here. So make sure there's space. Can I integrate this one? Okay, what's that going to be? Okay, this one. We can actually use your substitution here now. That's fantastic, right? So if I let u be x squared plus x plus 1, u is going to be 2x plus 1, right? Because the derivative of x squared is 2x, and the derivative of x is 1. 2x plus 1 dx. That's exactly what we have on top, right? So this part of the integral at least becomes the integral of just du over u, right? What's the integral of du over u? Natural log of u, which I guess maybe we should specify in the absolute value in this case, right? Plus the natural log of u, and what's u going to be? Plus x plus 1. Okay. And then okay, again, if you want to, you could combine these together. So this is actually pretty simple. There's not as many like numbers up front, so you could do like the natural log of x squared divided by x plus x over x plus 1 over x. So you like x plus 1 plus 1 over x. Okay, there we go. Any questions on that? I think that's enough. Okay, so obviously I don't want to take all the fun out of doing the problems. I want you to be able to do it yourself as well at some point. There is one more case, which is going to pop up a lot less frequently, but still happens, of course, which is going to be maybe I'll point this out here. This would be distinct quadratic factors, right? Because what happens yeah, absolutely. Right. So, yeah. So let's say that maybe I'll take this problem as an example. Instead of it being just x squared plus x plus 1, I would have x squared plus x plus 1 squared. Well, in this case, I would have a over x plus bx plus c over x squared plus x plus 1 plus, yes, and then just like in the repeating linear factor case, I would just have another one with ex plus e, or depending on which letter you're at, but it would have that term. Okay. And then from there you would work through the same process of working out. But again, very straightforward. I think again, these problems aren't the hardest, they're just tedious. Kind of the same thing with the, I feel like maybe tricky kind of hold that a little bit at times, especially with like that's the idea. Okay, so if that comes up, but do you feel like you attempted to kind of get through it? Again, I want to save some time here. It's going by pretty fast. I didn't feel like I've spoken this long, but it's taking almost as long as I did for the first sentence. Anyway, okay. See if there's anything else I have to say. There's going to be a section where you have to, maybe I'll do this, where you're going to have to make a substitution before you can do any sort of like partial fractions. Like that is still a partial fractions problem, but you have to kind of start out by fixing it in some way, right? So just to make sure that we can really understand the concept, I'll just use the one that they talk about, right? So if I give you this problem, this would be a little bit of maybe an interesting one to try to work out, because I mean, it doesn't have an x squared in here. So, at first you might think, oh, let me do, maybe I could try to do trig. substitution on that, but then you're gonna have a tangent squared, and then your dx is gonna get complicated. It wouldn't be very good with all the squares and stuff on it. Usually the sort of simpler is better in those cases, especially when just working with your trig functions. There's not really a clear winner for integration by parts here, nor is there. There's not, obviously, there's no trig functions now to even do trig integration, right? So instead, we're going to make a u substitution here. But not just, right? Because obviously, you can't say, oh, well, why would you do u substitution? You just let u be x plus 4. I mean, there's dx, but what about that x down there? Well, we can still do u substitution on this, right? Really, beyond what you get shown in class, u substitution is a lot more flexible. But you know, whenever you're teaching the calculus class, you really want to try to make it as graphic as possible. You know, because there's always all sorts of ways you can solve all sorts of problems, right? We have like 23 proofs for the Pythagorean theorem. I think actually maybe 30. I don't know. We have so many of them, right? But it's all to demonstrate that yes, it's the truth, and I have various ways to go about this, right? And u substitution is just another one of those tools that really has a lot of flexibility. To demonstrate in this case, we can let u be the square root of x plus 4. Okay. Now, again, it may seem like why would I do that in the first place? But I'll cover that in a sec. In the meantime, for the ones you do have like in the book, there's one that gives you like what exactly to put in, and other ones that should just be pretty straightforward. Like it's got normally where there should be x's, it's got cosines or sines in it. So you're like, oh, well, maybe let me replace all the sines with u or something. But sometimes you might come across something like this. So I want to work through it. So if I don't like the square root, I'm gonna name it something. I'm gonna let it be u. Okay. Now, from your experience, we might say, oh, well, I'll du that, and then we get some 1/2 square root of x plus 4, whatever, and then plug it in. But the issue is there's nothing to cancel that with. So what other option do I have? Well, if you remember from yesterday, we were talking about using trig, like integration or trig substitution. Instead of plugging in for, saying some expression equals u, you would let the x value equal something. So what I'm going to do is I'm going to take this and I'm going to solve it for x. So I have u equals the square root of x plus 4. So I'm going to take both sides, I'm going to square it, which gives me u squared equals x plus 4, which then leaves me with x equals u squared minus 4. So we get this, okay? Now, right, again, whenever we took the u sub, we say, okay, I have u, and then is there some way I can fit my du in here, make it work from what I have. But in this case, if I just solve for x, all I have to do is just see what dx is, right? Because with the x, I can plug it in both places, and I can take whatever dx is and plug it in for dx. What's dx going to be in my case? What's the derivative of u squared minus 4? 2. It's 2u du, not the minus 4 goes away. Remember, the derivative of the constant is 0, so that should be gone. Okay, so we get 2u du. Fantastic. Okay, so I'm going to take these things and I'm going to plug them in up here. This is going to give me, so u is the square root of x plus 4, right? And then we said x is u squared minus 4. And then we said dx is 2u du. And so we get this, right? Pretty interesting, right? Like that, I can just take, I just took this problem that had a square root and I said, no, I don't want a square root. So we might put it back in at the end, but now we have a rational function, right? Which when I multiply this u and this 2u together, I get 2u squared over u squared minus 4 du. Okay. So I could do partial fractions on this now, but maybe not quite at first, right? Is there something I need to do first? You need to do long division because the degrees are the same, right? They're equal, right? We talked about this earlier, right? If they're equal, you still have to divide it, right? So let's do this real fast. I'm going to take 2u squared and I'm going to divide it by u squared minus 4. So how many times does u squared go into 2u squared? Basically, u squared times what gives me 2u squared? 2. Good. So we're going to get, so we have 2 times u squared is 2u squared, 2 times 4 is 8. So that's minus, and then we subtract, which is going to give us positive 8. Okay, so we're going to be left with the integral of 2 plus 8 over, right, because I can't take u squared into 8 anymore, over u squared minus 4. Okay, which, right, what does u squared minus 4 factor into? Awesome. And we want this to be equal to 8 over u squared minus 4. What am I multiplying both sides by? So that's going to give me a times u minus 2 plus b times u plus 2 equals 8. Maybe I'll, maybe we'll go back to the method from earlier. Well, no, we'll stick with kind of a more standard way. So I'm going to have au plus bu minus 2a minus plus 2b, 8. Right? So what do we need a plus b to be equal to? 0. Good. Because there's no u over here, right? And what do we need negative 2a plus 2b to be equal to? 8. Awesome. So there's really a couple ways we can go about this. I might just do a quick substitution, right? Because I can solve this for b, for example. If I solve this for b, what do I get? B is minus a. So I get minus 2a, 8 is minus 4a equals 8. So what is a equal to? Negative 2. So what's b equal to? 2. So this is going to give us the integral of 2 minus 2 over u plus 2 plus 2 over u minus 2 du. What's the integral of 2? 2u. What's the integral of 2 over u plus 2? What's the integral of 2 over u minus 2? Let's see. Are we done? Why not? We got to put the u back in, right? Which is going to give us a final answer of 2 times the square root of x plus 4 minus 2 times the natural log of the square root of x plus 4 plus 2 times the natural log, the absolute value of the square root of x plus 4 minus 2, which isn't as necessary here, but so there's how a clever kind of use of idea, maybe change everything into something else, allowed us to work from now rather than what we started with. So, any questions on that? Yes, no, maybe so. Okay. You can take a break for about 10 minutes. We'll come back and we'll kind of wrap all this together. So we'll leave go. So 7.7, 7.8 are the relevant sections that are still going to be done in this chapter. 7.6 is going to be actual test. And then there is no 7.9. Yes. As of right now, I've only uploaded the video for 7.7. I really don't just not having a good chance to record 7.8. We'll have a video up, but I feel like it might be. So if you know, that's fine. But I'm gonna 7.6 agree. Okay, right. I guess it's not possible. It's well, no, I guess 7.6 is one of those like sections that's really like a kind of a compound section. I don't know that I mean, it's literally a table of integrals. So it's for the most part, you like have an integral like this. You look at it and say, oh, that looks like that's in the chart, and then you just write down what the chart says that the integral is. It's not exactly like that. Obviously, not every case is there, but and you do have to do use substitution so to get there, but it's just not. Yeah, we'll see that. I decided to wait for that, and I probably wouldn't even be able to put that on task because I'm not gonna be able to have you give you like a sheet with all those on it, you know. But I didn't want to mention it anyway, which will be okay because that next section probably chapter 8, beginning of chapter 9 we start. Probably detailed build. These rules really haven't been. There's just more examples, not as much like, you know, here's this idea, here's how to explain it.